So for problem number 2, we're supposed to be comparing and contrasting quadratic and cubic functions. And in this particular video, I'm going to do A and B. I've already done one of those in class, but I wanted to officially do A and B here in this video. So if we look at A, we can see that it's a parabola. It's got the vertex on the x-axis, and I will transfer that information over to this this piece of paper here. And again, we have a parabola that has a vertex. This is A. Again, we're going to do just part A. And you're supposed to draw the parabola just like it's drawn in on that extra sheet that there's a link to on Canvas. And then you're supposed to also write the equation of this cubic function. And the equation of the cubic function is y equals, it's a -2. So -2 times the quantity x minus 2 cubed. And then once you see that equation, you should quickly notice that this equation shows the graph of y equals x cubed shifted to the right 2 units and reflected over the x-axis. And so basically the graph moves down from left to right because the A is -2, so A is negative, and we have a third degree. So A is negative third degree, 2 units to the right of the regular y equals x cubed graph. Anyway, so without too much trouble, you should see that the graph of the cubic looks like that. And here we have the graph of the quadratic. The graph of the quadratic over here to the left of the y-axis. And so in the first statement, we see that it's saying that the domain of the function includes negative x values. Well, x is negative over here. We get over here and we get to x negative. Well, the domain is all real numbers for both of these. And so both of these functions, eventually the cubic will move over to the left of the y-axis, and so it will include negative x values. Anyway, here the function says the function is decreasing throughout its domain. Well, we could see here on the quadratic that it's increasing for part of the domain, so we're not going to put an x in that box. But here we could see this function is decreasing throughout, and so the cubic function is decreasing throughout its domain. Which function's x-intercept is larger? Well, this x-intercept is negative, this x-intercept is positive, so positive is bigger than a negative. And then this fourth statement, the function has a constant rate of change. That's a constant slope. The only time you're going to have a constant slope or a constant rate of change is if you have a constant function or a linear function. Those are constant rate of changes, meaning that the slope stays the same. This is a slope question. Well, here the slopes are different everywhere. The slope is negative on the left, positive on the right. Here we have the slope being negative, and then the slope is 0, and then the slope is negative again. It changes constantly, so neither one of those boxes gets an x. The function has an inflection point. An inflection point, again, is when you're curving down to then curving up. That's an inflection point. There's an inflection point there. You could be curving down like this and then curving up. It doesn't matter where it is as long as you're curving down then curving up, or curving up and then curving down, and that looks a lot like that. In fact, it is almost identical to that cubic function. And all cubic functions have an inflection point. No quadratic functions have inflection points. They have turning points, but no inflection points. The function has a minimum. We can clearly see we have a minimum on the quadratic, and then over here there's no minimum on the cubic. That the range is all real numbers. There's no minimum. And then over here the range of the function includes negative y values. So the range has negative y values. Well, yes, the range is all real numbers for the cubic, so therefore it always would have negative y values. But the quadratic here is not below the x-axis, and so there you go. That is all, and I will start another video for problem B, for the quadratic and cubic in row B.